Hello, analysis students. So I don't know if this will be chronologically the first lecture that happens in class, but it is the first lecture I'm recording. So you might have to forgive a few foibles that may happen. Additionally, this is not being recorded in any time similar to when class is happening. So there might be some pedagogical differences in terms of some of the presentation, but hopefully it'll be pretty close. All of this is also experimental. It's my first time doing this, so hopefully it works out okay. So this lecture will correspond to the lecture titled Limit Laws. It should be like the second or third lecture that we do on sequences. And in particular, I want to just focus on the proofs of two of the limit laws. One of them we did in class, and it's pretty straightforward. But let's go through it anyway, just to get some ideas of how to think about these things. So we're going to prove this. Let A and B be numbers, let A sub n and B sub n be convergent sequences. Suppose that A sub n converges to A and B sub n converges to E, then their sum converges to the sum of their limits. Fair enough. So let's kind of talk through an informal proof. So this will give us all of the ideas we need to compose the formal proof that will happen right here. So of course, what's going to happen? So the whole point of limits is that by taking this index n to be big enough, we can get A sub n minus A and B sub n minus B to be as small as we want. So we'll compose the proof as we go and figure out how small we need them to be. So let's go ahead and see how small we need them to be. So we can have control over A sub n minus A and B sub n minus B. We would like to control in that we would like to make it small, A sub n plus B sub n. That's the sequence we are interested in computing the limit of, minus A plus B. There's the thing that we think the limit is. And when we did this in class, probably much faster. This is already 2 minutes in. By just shuffling things around, you get A sub n minus A plus B sub n minus B. These parentheses don't matter, but that's okay. That's by just moving things around. And hey, look, that's something that we can control. We can make that as small as we want. We can make that as small as we want. By the triangle inequality, we can get this down to absolute value of A sub n minus A plus absolute B sub n minus B. We can make that as small as we want. So the kind of default thing, probably the thing that I'll do in class, is this, at this point, will just be called epsilon. And the second one, I'll say, well, that's less than epsilon. But hey, you look at that, it adds up to 2 epsilon, which is no good. So you divide everything by 2. Hey, that adds up to epsilon now. So we've concluded that A sub n plus B sub n minus A plus B is less than epsilon, as long as we happen to put an epsilon over 2 in all of the blanks. So there's the informal proof. Let's try to make this a little bit more formal. So let's prove this proposition. So since we're writing down a formal proof, we should start by all of the assumptions we have. Let's let A sub n and B sub n be numbers. Let A and B be numbers. A sub n and B sub n be convergent sequences. Let's assume that A sub n converges to A and B sub n converges to B. We must show that A sub n plus B sub n converges to A plus B. That is, we need to show that for all epsilon bigger than 0, there exists an n, which I think this time around in this class I'm going to emphasize that the n should be in the naturals. Technically it should be. Such that for all little n bigger than big N, absolute value of A sub n plus B sub n is the sequence, minus A plus B, there's the limit, is less than epsilon. So that's what we need to prove. We need to prove this. And I just walked a little bit away from the mic. Hopefully that didn't ruin the audio. So now what do we do? Well, we'll consider any epsilon because we want to prove something for every epsilon bigger than 0. Now we need to cook up a choice of big N. And we know very few things. We know, well, 2 things. We know A sub n converges to A and B sub n converges to B. Hey, both of those give us some big N's to choose. Since A sub n converges to A, there exists some N sub A, so that for little n bigger than big N sub A, comma, absolute value of A sub n minus A is less than any number we want. And in particular, we already know what number we want. We want that number. That's less than epsilon over 2. Similarly, since b sub n converges to b, there's some n sub b, so that for all little n bigger than big N sub b, absolute value of b sub n minus b is less than epsilon over 2. And now it's just a matter of adding the watts. So we've considered any epsilon. We've come up, well, no, we haven't come up with choice of big N. We've come up with two choices of big N's. Let's let big N, we want something that's bigger than both of them. So let's let big N be the max between n sub a and n sub b. And we'll see in a moment why that's the right thing to do. We've come up with the choice of big N. Now we need to prove something about every little n bigger than big N. Now consider any little n in the natural numbers and assume that little n is bigger than big N. Well, since little n is bigger than big N, and big N being the max of two things is bigger than or equal to each of those two things, in particular n sub a, we conclude, well, little n is bigger than big N sub a. So we can use this. We can conclude that the absolute value of a sub n minus a is less than epsilon over 2. Same reason, since little n is bigger than big N is bigger than or equal to big N sub b, that means little n is bigger than n sub b by transitivity. B sub n minus b is less than epsilon over 2. And I think I've given myself space on the next page. So we can put these two things together in exactly the same way as we did on the previous sheet to conclude that absolute value of a sub n plus b sub n minus a plus b, well, that's equal to the absolute value of a sub n minus a plus b sub n minus b. By the triangle inequality, that's less than or equal to absolute value of a sub n minus a plus absolute value of b sub n minus b. And maybe I'll even put the reason here just so you can read it. By the triangle inequality, and hey, a sub n minus a, that's less than epsilon over 2. B sub n minus b, that's less than epsilon over 2. So what do we get? We get that for all epsilon bigger than 0, there exists some big N. Right, we considered any epsilon bigger than 0 early on in the proof. I encourage you to flip back to that sheet. We've come up with a choice of big N. We then considered any little n bigger than big N. So that means we're showing something true for every epsilon and some big N and all little n bigger than big N. What do we prove? Absolute value of a sub n plus b sub n minus a plus b is less than epsilon. That's exactly what it means to have this limit statement. So now what I'm going to encourage you to do is I'm going to pause the recording. There will be another video uploaded synchronomously with this at the same time as this. And what I would like you to do now is there's lots of space right here. Compose a proof. If this isn't enough space, maybe it's not. That's okay. So I'm going to stop the video now. Hopefully it worked well. Stopping now.